And there's enough doubts that it's not clear that doggy theory is coming, but because it's a doggy theory, it's hard to push against it. So what Kun is definitely more accurate than this. Oh yeah. There is sort of inertia. At the very least, is inertia. Once you have a theory that seems to work, it's very hard to push. We're thinking like 70, like 5%. Sort of, but there is power. Comes still have on the margins, and it can eventually make its way to the center, but it takes time. It's not like it's open. It's not like every crackpot idea is working. You will. I mean, I think that they were more like why but I love way more money. I was at the big restaurant, so. It's called the yeah. So I remember getting on site, I have a lot of computer science. Yeah. Oh, yeah. You would afford it for me? You would afford it? No. Yeah, he might have that. So this is just a heavy. Yeah. Well, no, they didn't offer that. That's like the minimum. Yeah. I'll take it next week. Yeah, so is that early hands off? Well, it started. Oh, it started. Yeah, but it would have been very probably like. Yeah, right. Yeah, my age. Pretty good. Yeah. I think all the guys on your company are like just out of the show. Oh, really? Yeah. Oh, so the thing is that. Yeah. Wait, so where did you go? Oh. Florida can always be a small school. Florida? Yeah. Yeah. Like every. There's like any again. Is it like the Big Four or whatever? Or Final Four? Yeah, Final Four. Yeah. And then the championships. I'm not sure. I haven't called too much of the oh, okay. I think we do this. Yeah. I called too much. Yeah. Oh, it's yeah. Okay. So MaxCut. You've seen min cuts. This is MaxCut. You're given a graph. I give you weights on edges. And you want to disconnect the graph into two parts by deleting edges. And you want to do it by identifying a largest weight subset of edges as possible. So the min cut, you want to find the smallest capacity collection of edges that disconnects the graph. In MaxCut, you want to find the largest weight is capacity in this case, that disconnects the graph. Now there are many reasons why you want to do this. I won't get into them here. But this problem is not as easy as min cut. In fact, it's quite hard. It's a hard problem to solve. But that's not our goal today. Our goal is to understand how you might write this in a sort of a classical optimization framework where you have variable and objective and constraints. Okay. So let's think about how variables would look. If you want to encode this into some kind of generic optimization problem, where you want to optimize a function of a bunch of variables subject to constraints on those variables, what might the variables be for this problem? And again, think of the choices you're making. One way to think about this pictorially is to imagine that what you're asking is, really, if I have a graph G here, what you're looking for is a way to cut off edges so that you have them one side here and one side here, and then you have a bunch of edges in between, right? As many as possible. So you end up with something that you have two sides, vertices on either side of the graph, and then any edge between the two sides is part of this cut. So that, with that hint in mind, what might a variable well, maybe start more easily. What is the most obvious variable you should pick for this problem? Remember, variables encode choices. You're trying to make choices here. What would the choice be? What is a choice kind?
Edges.
Edges, right? So you imagine you might have one variable per edge, right? And how would we want to interpret the value of the variable? What might we want to say?
Actual value of the edge if they are crossing, and 0 if they are not crossing.
Well, I don't know what crossing is non-crossing.
Crossing.
What you mean is, did you pick this edge to be part of the
Yes, that's
cut
right.
or not? Right. So do you choose that you encode a 1 as the value of the variable for this edge if you chose to put it in your set, and you encode a value 0 if you did not choose. Okay, so let's start with that. So we'll say that the variable xe is equal to 1 if E belongs to S and if 0 otherwise. Okay. If we did that, what would our objective be? What is the goal of this optimization? Once we have this variable, assuming we have enough variables, what is our objective?
Maximize the weights.
How would I write that in an objective?
Sum of X into W.
Pardon me?
Sum of X in the weight into the weights W.
Right?
For
This will automatically pick up only the edges that are picked because they'll have a value of 1. Everything else will have value 0, so it'll work fine. Good. So now we've got our variables, we've got our constraint, we've got our objective. So we have variables, we've got our objective. Do we have any constraints? Yeah.
I'm sorry. On notation, can you scroll up a little bit?
Yeah.
What are those letters after such that? Is it G and E or
G minus E.
G minus?
Sorry, that notation is set minus.
Okay.
Yeah. It's also more of an abstract minus. I'm not actually subtracting E from G because G is not a set. G is a graph. This basically is a shorthand for delete all of E from G. So what are the constraints? Do we have any constraints on this? One way to check if you have a well-formed optimization is to say, well, if I don't put any constraints, do I still get a good answer? Right? Maybe that constraint problem is the right one. I see one head shaking. Is that a head shaking or just a head thinking? Okay, fine. Thinking is good. So do we need to put any constraints on this? Would it be fine the way it is? So I always find this helpful to say, okay, let's see what we can do now with no constraints. Can we solve this problem? This is maybe easy to solve because we know that unconstrained problems make it easier to solve. What is the solution to this problem? Set all edges. Is that right? Can we do that? If we set all edges, what is the problem? What in the original problem have we failed to achieve?
You just want 2 leftover components.
And if we take all the edges, we have no leftover components. So somehow taking all the edges is not going to work, even though it will maximize this optimization, which means there's something missing. And that tells us, okay, we need some rule for what is a valid choice of edges, which is, of course, our constraints. How would we write constraints? What is the constraint we're trying to encode, first of all? Remember the problem? The constraint we have to encode is that the removal of these edges, right, disconnects things into 2 or more parts. We didn't say 2, but we said just 2 or more parts. But clearly, if you remove one edge, you're not going to go from one component to 3 components. You're going to go from 1 to 2. So, how do you express that constraint here, though? I know which edges got picked because those are the variables that have value 1. How would I express this idea now that the graph is disconnected? Any thoughts?
Even if we pick all the edges, we still have two or more components in the graph, right?
You have
Each is
zero.
a discount.
If you remove every single edge from the graph,
Still the vertices exist, but they're not connected. So we have like, if there were any vertices, would it be a completely disconnected graph with just vertices?
that's true. Technically speaking, that's correct. Let me think, because that's not the spirit of what MaxCut is supposed to do. So I'm trying to figure out what I've said in the problem that is incorrect, that allows you to draw this perfectly valid conclusion from what I said the problem was. Yes?
Could you repeat that conclusion? I didn't understand.
Go ahead.
So what I'm saying is, even if we remove all the edges, we still have vertices. So it could be a completely disconnected graph, but it still has two or more parts.
Yeah. Yeah, so there were two, there's a couple of different ways to describe the MaxCut problem. I may have fallen into a way that is not quite accurate enough.
Remove all the edges?
Sorry?
Remove all the edges?
Yeah, she's correct. It will disconnect the
But
graph.
you want to up to
Right, but I didn't say that. I mean, she's perfect. I mean, I may have thought I wanted to say that, but I didn't say that. And so she's perfectly valid in saying you didn't say that. So it's my fault if this is not capturing what I wanted to capture. Right? I mean, this is a good, probe. Okay, you haven't said this right. So.
So a cut is not defined as creating two components?
Well, it is, but the point is that I claim that you can't take all the edges, and the answer is, well, why not? It just disconnects into everything. You have to all these individual things. The correct way to say this is what I should have said earlier, was, let me write it again, just so we can see. Find, actually this is what I should have said. Find S subset of B such that the sum of all edges belong to, I'll see what this means. Okay, there's a very complicated way of saying, find a subset of the vertices so that all the edges going out of that set, or that go across that set to the other side, the sum of those things is maximized. So this makes it more explicit. What I should have said was, this is the way I should have said this. I didn't say this properly. Okay? So again, the goal is to find a subset so that if you look at the edges between the subset and its complement, the number of edges is maximized. This takes care of your objection. Because now if I take away, what is my subset? Now the question is, what is the subset? Right? It's not, there's no longer a question of what the edge is, it's like, what is the subset I'm taking?
And we still can have more than two parts, so it will just be restricted to two parts.
I don't care. Find a subset. Yeah, so my subset itself could be disconnected. Right? But I just want to capture this. So good. So thank you. This was actually very helpful. So let's go back to our question now. How do we frame this as optimization now that I've changed the problem? And I mean, I know why I said it the other way. I was trying to fool you, and I ended up fooling myself. So that happens a lot. So how would you frame the variables now? I think that there's a bit of a clue here as to how you need to frame the variables. Because what is the choice you're making now? Now the choice you're making is the choice of the subset of the vertices. So what should your variable encode? Variables encode choices. So, yeah.
You would want to have.
Sorry, anyone? Yeah.
Go ahead.
Go ahead. You go.
Yeah, so vertices would be your choices.
Which means?
Which means that we set a vertex to 1 if it's in S and 0 if it is not in S.
Okay, good. what is our objective? How do we write down the objective? Because now we have variables for vertices. What do we say? Maybe you should start by asking, what do you want to say? In words, how would you write it?
You want to maximize those edges coming out of vertices which are going out of the subset.
Right. That's what we know we want to do. All we know is that xv is 1 and v is in the set, and xv is 0 if it's not.
For every edge are going from x to b, like some of the weights.
So for every edge going out of v, we have to do this for all v.
For xv is 1, like xv into wv.
Okay.
And summation.
Okay, let me write this up. So you want to write some summation over all vertices. Is that correct?
No, the ones in the subset.
Right, but since they're 1, then you can sum over everything. Only the ones that have a 1 will be counted. So let's start the summation. So you want to maximize sum over all v xv times something. Okay, what's something now? There could be other summations inside this if you want. What about it? Something like all edges coming out from v, right? Something like that. So we would write something like sum over all, I guess edges belonging to the neighborhood of v. Remember we talked about the neighborhood of v? W, something like that. Okay, what do people think? Is this a good objective? No?
Why do we need to write a modified objective, like the one which you do?
But the one before used a different kind of variable which you don't have anymore.
I meant like the one which you do by defining the problem here.
Here?
The better definition. This.
But how do I write this? We're trying to write this in the language of this because I don't know what S is. All I know is that some variables got set to 1. Right? So remember, my optimization objective has to be a function of the variables. So if I now look at this thing up here, this is not a function of variables because this is weird S. I don't know what S is. All I know is that I have these variables that are being interpreted as this way. My optimization doesn't see this. It only sees this. So the question is, how do you translate that into something that only uses this? That makes sense? And our proposal is to do this. Our claim is that this thing here is exactly that.
So if you transform the variables there a bit, for example, you say for every edge belonging to vertices u comma t, then t is a vertex on which the edge is incident into.
That's a lot of words.
So that
And I have no idea what they mean. Try again.
So summation over all.
So are you complaining about this objective?
So I'm saying like it doesn't capture one thing.
It's missing something.
It's missing something.
Okay, it's got a bug.
Yeah.
Tell me the bug.
So the bug is that it's not counting those edges which it only has to count those edges which are going out of the subset. Correct. This is not doing that.
What is it doing?
So
Where is it giving a bug?
this is checking all the neighborhoods. So it will also check all the edges which are into the set.
Okay, so the concrete objection to this function right now is that it will, so if I drew my graph partitioning out, these are all the zeros and these are all the ones, it's also going to count an edge here, which it should not count because it's not part of the cut, but it will count because it's looking at everything in the neighborhood. Okay, we need to fix this. How do we fix this?
What if we only say xv is 1 when it is actually an edge? Like when that vertex actually has an edge going out.
What does out mean in the language of the variables? We are only allowed to use the language of the variables.
So when there is an edge which connects two components, one in S and one is V, one in
I don't know what S is.
the set and the.
I don't know what S is. All I can see are variables. Give me in the language of the variables.
can create one more variable.
You want to create a variable?
for the
Okay.
Edges, which should be having, which will be checking for the vertices in front of it.
No, that's too many words. What is a variable? There's a variable e. There's a variable xe, and the variable is some value. If some, tell me.
Instead of summing up all those edges,
Yeah.
I'll create one more variable which will be like a filter saying that if one
Wait, you're creating a variable that will be a filter. That's what you're saying.
like a 0 and 1, the
Sure, yeah.
edge values be a 0 and 1
Okay.
for each edge, and then I'll say that that edge value is 1 if one of its vertices is in 1 and the other vertex is not in
So what you're saying is you want to create an auxiliary variable. Let's call it x. Let's call it xe. Well, I don't call it xe. Let's call it ye. So that ye is equal to 1 if. So let's say e is equal to u comma v. If u equal to 1, v equal to 0, or v equal to 1, u equal to 0, and is equal to 0 otherwise, right?
Yeah.
Great. But I don't have the luxury of this language. This is logic. In an optimization, I am not allowed to use those kinds of things. I have to use algebra. How do you encode this in algebra? Yes.
So summing over all the edges in the cut, where each edge goes from a vertex u to a vertex v, summing over x of u into we plus x of v, we should be equal to we. Should be equal to the summation of h over v.
Lucky one.
So let's say an edge belongs to the cut, right? And this edge is between 0 and u and v, right? Now we say that.
So you're summing over all edges in the graph right now?
Yeah.
Okay, that's fine.
Not all.
You can't sum over the cut. We don't know the cut. In the language of the optimization, we don't know yet.
Okay, let's say that yes.
Right.
Yeah. Okay. XU WV plus XV WV has to be equal to the same summation of
There's a constraint on the choice of the vertices.
yeah. This makes sure that only one of these is 1, right?
Why? I could oversubscribe on one thing and undersubscribe on another one. You're just saying the summation should be the same.
How about XU plus XV?
Write it. Don't tell me to write it. Can't write it, I can't be stupid.
And we have one more constraint on this that XU plus XV is equal to.
XU plus XV must be equal to 1. So you must pick one endpoint of every edge.
One of them should be in the subsets.
Why?
That's how the cut will be.
No. That assumes that every edge must be in the max cut. You're trying to see if there's a way for every edge to be in the cut. Suppose you have two vertices on one side of the cut, then both of them could be 0. And you're insisting, no, that cannot be 0. You're saying that's not feasible, but it is feasible. That doesn't work either.
Yeah.
So let's go back to ye. I think people are very quick to abandon the ye. I kind of like ye. It's a new variable. We want to be friendly to a new variable. So can you encode this algebraically? Here's what you want to do.
The same thing like what he wrote, the second one.
Okay.
The xv plus here, if u plus v equals to 1, then keep it as 1, or it's so instead of doing it as like
So you're saying.
or else condition.
So you're saying set ye equal to xu plus xv. Is that correct?
No.
No? Okay.
be 1 plus 1.
That won't work. Yeah.
That doesn't work. So,
So by the way, this is an AND condition, right? Both of these things must be true.
oh, it's an X, we can use an XOR condition.
Multiplication.
Continue. XOR. Continue the thought. So YE should be right. So you're saying that YE. What you're really saying is Y is equal to XU XOR XV. Is that correct?
Yes.
How do we express that algebraically? You've established the correct logical condition. You need to write this in the form of a function.
Right,
So we know what. So we all know that XOR can be written in terms of AND or NAND. We know how to write an AND, which is multiplication. So how do you write an XOR?
XU into 1 minus XB plus.
Okay. So what do you right?
Plus XB into 1.
Okay. Well, let's try this out. Let's make our little truth table. Yeah. Okay, so in the case of both being 0, this is clearly 0. In the case of both being 1, this is clearly 0, because the inside terms go to 0. In the case of one of them being 1 and one of them being 0, one of the terms survives. You got it? Okay, but now what do we do? Now we've got YE, which captures, so we know that YE is 1 if the edge is in the cut. This is a very important thing. We've been struggling to do this somehow. Now we've got it. Okay, now what does the object look like?
Multiply y to W.
So now our new objective is going to be maximize what? What's our maximization?
The above equation what we do, just multiply.
But you need that complicated above equation with neighborhoods and stuff. You may not need it anymore. We have, remember, Y is telling us which edges are on the cut.
Yeah.
So what do we have to do?
Y into W.
Sum of y.
Y into W.
Yeah, so you can think of it as maximize the sum of the weight over the condition that the edge is in the cut, which we can just immediately, we don't even have to add the extra variable. We can just write it as XU times 1 minus XV plus XV times 1 minus XU. Do we have any constraints? Beyond the fact that XU should be in the set 0, 1. So every xi has to be in the set 0, 1. That's assumed. Right? XV, no, not assumed, it's a constraint. Is there any other constraints we need now? Well, if there's no other constraints, we can sort of try to prove that this is correct now. So once again, suppose we have, so let's just check if we have a cut of value, whatever, some value, let's say W, because a certain number of edges get in the cut, what will be the value of this optimization function? Well, we have chosen, we will choose one side of the cut to be the things we label 0 arbitrarily. We'll choose the other side of the cut to be the things we label 1 arbitrarily, right? By definition, this construction will pick off only edges that are going from the side 0 to 1, vice versa. And this will be the exact value of that cut. So every cut of a certain value will give us the same value objective here. That's step 1, right? Similarly, if any feasible solution here, right? Any feasible solution here, forget this maximization right now, right? We'll have a certain cut value, which corresponds exactly to the size of the cut there, just by the construction here. Which means that a feasible solution to the feasible solution for the optimization where things are validly set to 0 and 1 gives you an objective whose value equals the value of the cut you would get if you in fact put those vertices on 0 and 1. So every feasible solution here gives you a feasible solution here, every feasible solution here gives you one there of the same value. Therefore, maximizing that is the same as maximizing this, and maximizing this is the same as maximizing that. Therefore, this in fact is MaxCut in optimization form. Yes?
So when we were solving the minimum cut problem, we were only considering the value of the edges which are coming out of the set, right? But here we are also considering the...
Well, there's no direction.
Yeah.
It's an undirected direction.
Okay.
When you looked at the randomized MaxCut,
Yeah.
then there was no direction.
But when
For
you
ST MaxCut, for directed graphs, there was a direction. And there was looking at capacities. But here I'm just saying, look, let's look at the edges between the two sets, not one way or the other. There's a little observation you can make here. We chose the xv's to be 0 and 1, and we got this function. If I instead chose the xv's to be -1 and +1, so -1 encodes one side and +1 encodes the other side, you could actually simplify this expression. So suppose instead, and this is just a way to illustrate how changing the encoding can change the problem a bit. And you can verify that this is true. Then our objective becomes maximize summation WE 1 minus XU XV divided by 2. So one way to see this is that if they are the same value, you get 0. If they are different values, this becomes -1. 1 minus -1 becomes 2 divided by 2 gives you 1. So it's a slightly cleaner version of that. It doesn't make too much of a difference, but subtle changes in coding can change the objective. That's also a good thing to know, that you have some discretionary power in your concepts. There's another very interesting thing which you can see in both of them, and it's probably very clear in the second formulation, that this is not a function we've seen so far. This is a function where the objective now is not a linear function of the variables. It's a quadratic function of the variables because they appear multiplied together. That's not something we've seen before. And that's already a warning sign, oh, this is going to be a problem. And in fact, it is a problem. MaxCut is not an easy problem to solve. It's intractable. It's NP hard. I'm not saying that this makes it NP hard. I'm just saying that this is a sign that it may not be as simple as the ones where it is all linear. And sometimes that happens. So the problem is that. And you could spend some time trying to figure out how to not make this quadratic, but you will in all likelihood fail because in all likelihood, MaxCut is not in polynomial type. So there's unlikely to be a linear version of this. Okay. So that sort of concludes my first sort of part of our discussion here, where I sort of wanted to show you different ways of thinking about the problem of optimization, which basically involves variables, an objective function, which is a function of those variables, and constraints that limit the feasible values of those variables, right? And this is a very sort of abstract way of thinking about a problem. There are no graphs here anymore, right? There are no graphs, there's no cuts, there's nothing. There's just an objective function. This is important because the whole point is to funnel all my different kinds of problems into this standard objective formulation, so that I can then optimization formulation, so I can then solve it. It also means that problems that don't look similar might end up looking similar once you write them in this form. In some sense, all of machine learning becomes a certain kinds of convex optimization. Yes?
The variable xv we originally defined to be 1 for vertices in the subset S, correct?
Right. So another way to say this is that now in the new encoding, right, here, xv is equal to 1 if v is in S, and is equal to -1 if v is in v minus S.
So I guess my question was actually for previously, how do we define xu? Like, can you clarify what xu is?
So all I'm saying is xu is a variable. We have one variable for every vertex. So if our graph had n vertices, we're going to construct an instance of an optimization with n variables. We are allowing the variables to be either 0 or 1. That's a constraint, right? That they get to choose to be either 0 or 1. We are interpreting a 0 or a 1 as being not in the set or in the set. But the optimization doesn't know anything about that. It's just like, okay, it could be 0 or 1. That's my constraint. I'm going to try and figure out values for it. It's what we interpret those values as being is what gives us a solution to the original problem.
and the edge is defined by the pair, that pair of vertices.
The edge is defined by the
Pair
pair.
of XU or XV, like the XU, XV.
I don't know what you mean. What do you mean by the edge is defined? The graph has edges. The optimization problem has no edges.
An
in it.
edge is
There's no edge in the optimization, right? There is a variable that encodes the idea that an edge, that encodes a consistent sort of interpretation of whether you choose one vertex. So if you choose one vertex and you don't choose the other one, then the edge between them is the cut. That's in the language of the graph problem. In the language of the optimization, if XU is 1 and XV is 0, then YE will be 1.
Yes, okay.
That's all.
Understood.
Right? Was that kind of where you were going with this?
Yes.
Okay.
Yeah.
Yeah, so we have to remember that we have to interpret, we have to express everything in the language of function of optimization and interpret it in the language that we want. So that's what the modeling process is about. You translate the original problem into this sort of more abstract language in such a way that this captures the problem you're looking at. This is the essence of all modeling. The reason why optimization is important is because so many problems can be funneled into that same modeling paradigm. Okay? All right. So if you draw kind of a taxonomy, right? So if you say, okay, let's look at variables are just variables. Okay, well, we'll do this as well. Constraints, variables, and objective. Depending on what happens to these things, the problem can get easy or difficult. It's kind of it's a strange. For example, in general, variables can be discrete or they can be continuous. This is bad, and this is generally good, generally speaking. Objectives can be linear, quadratic, convex, non-convex, right? Linear is generally good, convex is generally good, non-convex is generally bad, and quadratic is kind of a depends. Okay?
So by discrete variable, you mean
The variable takes discrete values, like 0 or 1, -1 or 1.
continuous is floating?
1, 2, 3, 4, 5.
Continuous is like floating point?
Continuous is continuous. Floating point is not continuous. Floating point is discrete. Don't say floating point. Continuous is continuous. Any x can take any value on 3, 0, and 1. Any real value.
Okay.
There's a whole issue of how you actually compute these things. I'm not going to get to that. I may never get to that. That's much tricky. Okay, so that's our variable. So, and what about constraints? Let me just move this down because I don't know. So constraints can be linear. They can be they can be nonlinear in general. There's a subclass of this called semi-definite, which I will explain in a little while. And again, here we're happy. Here we're generally not happy. And here, surprisingly, even though it's nonlinear, we're kind of happy. So, of course, these all combine up, right? So, depending on what your variables look like, what your objective looks like, and what your constraints look like, you will get a different kind of optimization scenario, which might require its own kind of solution. For example, all variables linear, all variables continuous, all objectives, the objective is linear, constraints are linear, you get something called linear programming. Variables discrete, objective linear, constraints are linear, you get something called integer programming or integer linear programming. Variables continuous, objective convex, constraints linear, you get something called convex programming, which again is Google. And all of these have their own sort of technique. Obviously, the more general ones can be used to solve the more specific ones, but sometimes the more specific ones have better methods that work because you know more about the problem. Okay? And so you have a lot of choice in your optimization in how you model a problem. But of course, you want to choose to model it in such a way that you get to the easiest version possible. So you'd like to be, linear, and continuous. That we can solve. Failing that, you might want to be, I don't know, semi-definite constraints and linear objective or something like that. There are games you can play. And again, we won't cover the entire spectrum of what you can do, but we'll focus on a few key ones. And then the key one that we're going to focus on next is linear programming.
Yeah, sure. When you said that continuous variables are good, does it mean
Generally
like,
speaking.
yeah? So like, does it mean like if in max flow problem we allow the capacity and the flow to be decimal, then it would be then it would give us a better solution than what we have been seeing?
Flows are tricky because it turns out even though if you have integer capacities on your problem, even if you write the flow problem as an optimization without any constraints on the variables, allowing them to be continuous, they will end up being integers. So rather than saying I require integer flow, you can just say I don't care. Give me a continuous flow, and by magic you will get integer flow. So flow is very nice that way. It's a subclass of linear programming where the solutions are guaranteed to be integer.
If the capacity is right.
Yes. And as we've seen, I think I've mentioned this, that if required is not equal, that's right. And we kind of implicitly showed that with Ford Fulkerson. That we showed that if all the capacity is integral, you can always keep making progress with integer flow until you get the answer.
If the capacities are not integral and we run the max flow, what happens like?
What max flow are you running?
Do we have a
Which max flow are you running?
any max flow algorithm?
I think I meant, well, it depends, but if you run Ford Fulkerson, I mentioned this, that you can actually get bad answers. Okay, you get wrong answers. You can converge to a completely wrong answer. The notes actually have an example of this. So basically, the correct answer is some arbitrarily large number, but what you converge to is a number that's less than 7, regardless of what the actual flow is. If it's all irrational, if you use irrational numbers, for example. It's a very clever trick involving Fibonacci. So yeah, so that's why there's a lot more nuance and sophistication in how we think about this landscape. But the dimensions of how we think about this are basically along these lines. So when you are thinking about optimization, you should be asking yourself, okay, how are my variables constrained? What do my constraints look like? How are my variables defined? What do my constraints look like? And what does my objective look like? And that sort of classifies you into a certain territory of what kind of optimization you're going to end up using. So for example, most of deep learning involves non-convex optimization over continuous variables. Generally speaking, there aren't any constraints, but sometimes they can be. It makes it even harder. But that's that's like the hardest of the hard thing to deal with. So for those problems, you can't always guarantee to get optimal solutions. You can only guarantee something. So like I said, you could do a whole course on this, which we're not going to do. But there are courses in the university that offer this. What I want to focus on, because I think it's one of the most important optimization frameworks that occurs in algorithms, right, is what is called linear programming. Linear programming is characterized by continuous variables, linear objective, linear constraints. Okay. For the longest time, we did not know whether we could solve linear programming in polynomial types. In fact, the early versions of the book on NP completeness from the 70s left this as an open problem. And then in the late 70s, and then again following that in the early 80s, 2 algorithms came out that showed that you could solve this linear programming in polynomial type. So that's good, because then if we can take a problem and convert it to linear programming, we know that there's a polynomial time solution for linear programming. That means our problem has a polynomial time solution. So it helps us to try and translate whatever we're looking to into the language of linear programming. Okay. So, what does a linear program come? Well, you have variables. They're unconstrained. They could be between 0 and 1, but it doesn't really matter. There's just R. So you have variables x1 through xn. There's a linear objective. Well, any linear function of n variables can be written as summation of ci xi. Right? This is a linear function of the variables. If there's an extra constant, that doesn't matter in terms of optimization. And you can either maximize or minimize, doesn't matter, because I can merely just multiply the constants by -1 to go from a maximization to minimization. Okay. So in general, we can see that this objective is going to look something like maximize. And I'm going to do something very tricky here. I'm going to write this as C transpose X. Think of X as a vector. Think of C as a vector. We're taking the dot product of C and X. Okay? Which you can write in matrix language as C transpose X. C. If C and X are vectors, C transpose becomes that, and just like that. It's a convenient shorthand for that summation. It will also be important because this shorthand will give us some geometric intuition about this problem, which will be very helpful. So we're going to maximize some C transpose. Okay, C and X are vectors here. I don't want to clutter it up by putting vector notation top, but keep in mind that. But there are also linear constraints. So what would a linear constraint on a bunch of variables look like? A linear constraint might look like, I don't know, summation AI xi is less than equal to b, for example, right? Add up a bunch of the variables, some of these AIs could be 0, then their sum should be less than equal to something. That's a linear constraint. It's a linear function, and you have some constraint like this. It could be greater than equal to something. It could be equal to something, right? If you want to write an equality constraint using this, you can merely say that, so we can write sigma AI xi is equal to b corresponds to the two constraints. Sigma AI xi is less than equal to b, and sigma AI xi is greater than equal to b. And we can always do greater than by minus sign. So without loss of generality, we can express any constraint that looks like this. But there could be more of them, right? There may not be just one constraint. There could be a whole bunch of them. So in general, you could have, you could have sigma A1I xi less than equal to b1. You could have sigma A2I xi less than equal to b2, and so on. You could have as many as you have constraints. More generally, you can write this as something like a matrix A times x is less than equal to some other vector. Right? If you just stack up all these individual row constraints together. So the full generalized form of a linear program looks like linear objective, continuous variables, linear constraints. And what we will look at is, what we will progressively look at is what this means, geometrically speaking, what it looks like, and then some ideas of how to take a problem and translate this into this language. Because once we do, we can solve this problem. So this is a very abstract formulation, right? This has no context. We don't know what problem we might be solving, and that's the power. It's a general context, a general language to express optimizations, which has a known good solution. Okay. All right. That's it for today.
See you all Friday. Lynn, I have a question.
Yeah.
When will Homework 5 be released?
I was hoping to release it tonight. If not, it'll be to run tomorrow.
Okay. And then 6 will be 2 weeks.
Yeah. So 5 might be a bit shorter because it's randomness, and I don't want to scare you all. So I might be sending you your homework. So I could really mess with your minds to randomness.